Hello, my name is Rawson, and for my summer 2022 REU experience, I furthered the research of cryogel and aerogel insulation for cryogenic applications. I'm continuing the research of Alan Sherman, and I worked alongside Garrett Hauser and Chaley Benyako under our mentor, Dr. Mark Meisel. There we go. So what our focus of our research was to look into the magnetic properties of cryogel. There's interest in using cryogel in insulation technologies in the field of NMR and MRI, as well as like particle spectrometry, because between the cryo-cooled coils of the electromagnets and the bore of the magnet, if you're going to put anything in it, you need to protect the temperature difference between them if you're putting things like live animals or living tissues within them, as well as just to keep the superconducting properties of the electromagnet intact. So in order to use cryogel in these applications, we have to analyze its magnetic properties at high field and through a range of temperatures. So we did this using a Squid magnetometer. Squid stands for superconducting quantum interference device. And how it works is that inside the bore of a superconducting electromagnet, there's these superconducting wire loops. And whenever you pass the material through these wire loops, the change in flux induces this, this voltage, this induced current. And the computer takes this induced current and voltage and transforms it into a magnetic moment of the material. So you can subject it to different temperatures from 2 Kelvin to 390 Kelvin, which is almost boiling. And you can also subject it to up to 7 Tesla. So the results from this, I did 2 different tests. One of them was holding the magnetic field constant at 1 kilogauss, getting the susceptibility versus the temperature. And then the second one was holding the temperature constant at 5 Kelvin and doing a magnetization versus magnetic field. And we did the susceptibility versus temperature first, and we found this distinct Curie tail below 50 Kelvin, which is not what we were expecting because cryogel is a silica aerogel and silica is diamagnetic, and usually you would just see this negative constant horizontal line at high temperatures. So to go into more detail about what was causing this Curie tail to form, we went to 5 Kelvin. We did magnetization versus field, and I graphed 2 different fits using a Brillouin function. One of them, this dashed line, is spin 1/2, and this red line is spin 5/2. And you can see that the red line much better fits this data. So this gives credence to the theory that there's possibly iron contamination within cryogel. As Garrett explained earlier, pyrogel contains iron oxide. So we think that there could be iron contamination between the 2 different types of gels. So in conclusion, we found a positive magnetic contribution at low temperature, and it's likely some form of contaminant, likely iron. The expected diamagnetic properties are overshadowed by this positive magnetic contribution, but at high magnetic field, you can actually see the slope of the Brillouin function or our data go down in this negative slope, which I think points to the diamagnetic properties of the silica dioxide fighting against the positive contaminant, whatever it may be. So next, what we want to do is we want to analyze cryogel's magnetic behavior with respect to frequency so that it may be used in NMR and MRI, and also further tests on its dielectric properties. I want to thank Dr. Kwana Johnson, as well as my mentor and the National High Magnetic Field Laboratory for giving me this experience. Thank you so much.